A trigger is a fragment of code that you tell Oracle to run before or after a table is modified. A trigger has the power to, and it goes on and talking about it, fixing a Macintosh so that it doesn't crash when you connect it to the internet. And I don't know how many of you have met Eve there over at ours. Digita, a friend of Phil's. But anyway, today we're going to talk about a bunch of stuff, including how the trigger mechanism in a AR-15 works, and in fact in most semi-automatic weapons. And so you'll come out of here at least knowing something of value.
But we are stockpiling weapons. So we have to stockpile weapons. I know a lot of people that find this
But what's neat is that you're actually going to see the connection between mechanical mechanisms like that and all sorts of electronic devices such as the ones that we're going to talk about today. So what we're going to be doing right now, in the last lecture we took a general look at finite state machines, okay? And they were called synchronous finite state machines because the state transitions happened in synchrony with a periodic clock, right? Every so many billionths of a second, what have you, the system would transit from the present state to the next state. And I saw on the blackboard that in your recitation you talked a lot about figuring out the timing of that and got a little more practice with that. You will get more practice in the problem set next week. And I saw some nice state diagrams here too as well. What we're going to do now is we're going to go kind of underneath the hood of that thing, and ultimately we're going to figure out how to design that flip-flop or that clocked register that actually holds the memory of what state we're in now, and on the rising edge of the clock switches from the current state to the next state. And we'll talk about guns as well. Sure. How many people here fool around with guns? Just so I know. 1, 2, 3. Okay.
Guns and dancing.
So for a while before I got fed up with the NRA, I was actually a simultaneous member of the ACLU and the NRA at the same time. But, you know, then they kind of went nuts, and so I said, okay, forget those guys. And I stuck with the ACLU. Some people think they're nuts too, but they're wrong. Okay, what do these things have in common? Well, keep these in the back of your mind. We're going to talk about the trigger mechanism on the inside of semi-automatic weapons. Like I said, we're going to talk about airlocks, where an astronaut goes inside and outside of a space capsule. We're going to talk about something called an escapement mechanism that's part of a clock that works like this. And finally, we're going to talk about our old friend, the flip-flop, or the register, which is clocked by an edge. And you're going to see how these are all, in fact, quite similar. But let's go back a little bit to these fundamental elements we talked about before. In particular, let's take a look at the selector. The selector, remember, was something that had a control input S over here that said whether we select A or whether we select B. And if S is 0, in this case, we choose A to go out to Q. If S is 1, then we choose B to go out to Q. And if we take a look at the truth table of this, it's really quite simple. If S is 0, Q is A. If S is 1, Q is B. Now, moving along to kind of explore how this selector actually works, excuse me, in terms of the K-map and the possible values of A and B, if you draw it out, you end up with this beautiful K-map. And notice the dropped boxes here. You know, I'm getting really fancy. That sort of fills in all the zeros and ones. So here's A. This is where A is true. And here in these two columns, here's where B is true. And if S is 0, then the output Q is equal to B. You see that here. And if S is 1, then the output Q is equal to A. And you see that over here. Now, the question is how to actually build a selector out of AND gates and OR gates and possibly inverters. In other words, to do a sum of products implementation of a selector. Well, the first thing that you might be tempted to do is say, well, I want to make circles of product terms that are a power of 2 in size and as large as possible, and I want to sort of use the minimum number of them to cover all of the ones that are in the circuit. In other words, I want to minimize the number of AND gates that I use. So you might come up with an implementation that looks like this. I'm going to circle these two ones over here. That's product term number 2. And I'll circle these two terms over here. That's product term number 1. And if I implemented two AND terms that fired in this case or in this case, then I will have implemented the complete K-map for a selector.
This K-map is not the same as the previous one.
Did I do it differently?
Yeah.
Uh-oh. Another mistake, huh? 1, 1 in the middle, 1, 1 on the right. A and B. A is true when S is 1. A is true. What did I do wrong?
The second one matches your circle.
I flipped A and B, okay? So I'm sorry, I made an error here. So I switched around what the role of A and B were. So S is 0, it chooses A. S is 1, it chooses B. So this is correct, right? Let's go back and see what I did wrong. S is 0. Oh, okay, this is wrong, right? The truth table over there says S is 0, it chooses A. And here, S is 1, it chooses A. So take this one and move it over to here, and take this one and move it over to there. This is the one that's the error. See, I shouldn't have added these fancy things because it distracted me from the truth here. This is what it should look like. Okay, so this is the correct K-map. You guys are so much more attentive than MIT students. It's just amazing, okay? Because they all slept through all this stuff. So. Okay, how do we actually implement this thing according to that K-map? We have two product terms, P1 and P2, consisting of two AND gates. Here's the AND gate P2, here's the AND gate P1. And notice what this says is that if S is high and B is high, then P1 is going to be high, which will go into this OR gate and make Q be high. On the other hand, if S is low, then this will be high, and A will be high. By high, I, in this case, mean a logic 1, and by low, I mean a logic 0. Then both of these will be high, and P2 will fire, go through this OR gate, and we will get a high value on the Q output. So this is, again, sum of products form. Here's the OR, here's the AND, and here's the inversion that you might want to do on some of them. Yeah?
Can you just say again where you can tell if S is high or low?
Sure. Sure. Here, if the logic convention I'm going to use by default, unless we say otherwise, is that a high value or a high voltage is equivalent to a 1, and a low voltage is equivalent to a 0. Now, later on in the course, we're going to talk about sometimes when you want to flip that. But by default, just assume that we're going to use what's called positive logic, which is high equals 1, low equals 0. If S is a 1, then the AND of 1 plus 1, excuse me, and 1 is 1. And then the OR of 1 and anything else is going to be 1. So the key thing to realize that if P1 fires, if P1 is high or if P1 is a 1, what that means is that it doesn't care about P2. And P1 will be responsible for holding Q high, or Q to be 1. On the other hand, if S is low, if S is a 0, then this value over here will be high, or a 1, because this is an inverter over here that switches the logic polarity from input to output. And so if that's true and A is true, then P2 will be true, and that will be sufficient to hold the output high all the time. Yeah?
This is just a, sorry.
P1 and P2 will never both be 1. Right?
At the same time.
Right.
Well, that's probably true, except you have to think a little bit about the timing of things, and we're going to talk about that in just a few seconds, okay, when things are changing and one of them is going high and the other one is going low. But, in fact, you're absolutely right, because if you go back to the K-map, you'll notice that P1 and P2 are circles in mutually exclusive parts of the K-map, okay? P1 fires when? When S is 1 and when B is 1. Okay? P2 fires when S is 0 and A is 1. And that's exactly the logic that you have in the diagram here.
Well, this amounts to just A or B.
Well, it's not exactly A or B because it depends on S also. You see, here's another way to think about it, guys. What does an AND gate really do? Okay? A comes in here, and let's say that A is wiggling back and forth between a 1 and a 0. Okay? So there's a signal on A that keeps switching back and forth between a 1 and a 0. If this input to the AND gate is 1, then that signal on A will propagate through to P2. Because 1 and A is equal to A, right? If you AND anything with 1, you get the same thing back. On the other hand, if this signal drops down to 0, then whatever A is doesn't matter because the output will be 0. So this is really kind of a gate in the real true sense, where if this is high, it's a gate that allows A to go through. And if the gate is low, it prevents A from going through and forces a 0 on the output. So that's another way to think about a AND gate. And in fact, the word gate comes from that because it's really functioning as a gate to let A through if this is 1, and to just force this to be 0 if this is a 0. Kind of makes sense? Yeah?
Yeah, I can see now how the AND gate works, but how does the inverter work? Because it either takes away charge or it adds charge, right?
Well, not exactly. This is the input side of the inverter, and this is the output side of the inverter here. So when there's a logic 0 here, a short time afterwards, a logic 1 is created over here. And when there's a logic 1 over here, a short time later, a logic 0 is created over here. So it's like an amplifier in that it takes an input signal and replicates it on the output, but it does an inversion of the signal. Okay, so it's not that there's one place where charge is being generated or taken away, and there's no memory per se on the inside of this thing either. It's just a logic function that's sort of taking the input, reversing it between 0 and 1, and then propagating it to the output. Does that sort of make more sense?
How does this differ from A or B?
How does this differ from A or B? Well, if S is 1, then this will be 1 over here. This will be 0 over here. And this circuit's output will not care what A is, because the 0 will close the gate over here. And the 1 will open the gate over here and allow B to flow through to the output. Does that make sense? Let me actually put this on the board. So let me just get it exactly the same here. Here's S. Here's B. Here's A. Okay, now let's just think about this circuit so far. Okay? If S is 1 and B is 1, then the output's going to be 1. Okay, if S is 1 and B is 0, then the output's going to be 0. Okay, so that's good. Okay, that's one case. Now, let's switch to the purple chalk. If S is 0 and B is anything, doesn't matter. What's the output going to be? 0. Okay, good. Now, so what's going on here? Only if S is 1 does it allow B to propagate through. If S is 1, the AND of 1 plus B, or excuse me, 1 and B is going to be B on the output. So this is selecting B to be allowed to go through. You can think of an AND gate in those terms. Looks like I have mail. Okay. But if S is 0, it blocks B from going through and forces the output to be 0. So it's an AND gate, where the gate is gating whether or not this thing goes through. A really easy way to see this, if you guys had a hardware setup, would be to insert an audio signal over here in digitized form, or a video signal in digitized form on B over here. And if you made S turn on, if S was a 1, you'd see the signal over here too. You'd see the picture, or you'd hear the sound. And if you made S be 0, it would click off, and you'd only get 0 on the output all the time. Okay, now this AND gate works the same way. It's going to gate whether or not A is allowed to go through. And that gate is going to be determined not by S, but by S bar, by the inverse of S. So when S is low, A will be allowed to gate through. And when S is 1, B will be allowed to gate through. And then what we do with these two outputs is we combine them with an OR gate, so whichever one is being gated through, either A or B. And notice only one of them will be gated through and the other one will be at a 0, because when this is low, this is high, and when this is high, this is low, right? Then the output of the selector will come out here, Q. Does this kind of make sense now? A little more?
Does that differ from A or B?
How does it differ from A or B?
If A is true and both S and B are false.
What if A is a 1, B is a 0, okay? A or B says that this will always be 1. But here it depends on S. That's how it differs. Other questions? Yeah?
When you get a chance, could you go to the next, or I'm sorry, the previous slide, and when
Sure.
we had the K-map up there, is there any meaning to reading across a row of that Carnot map, like one row, because 0, 1, 1, 0, does that stand for something?
Sure. It stands for the fact that in these middle two boxes, it's 1, meaning that the output of the selector will be 1 in the cases where S is 1 and B is 1.
Okay,
That's in those two. And in the other two, it's going to be 0.
but that group, 0, 1, 1, 0 doesn't stand for anything?
No, no, no.
Other than the individual elements?
Other than the individual ones, right. And then when we circle the two ones together, instead of separately. So if I were to just circle this one over here, this would be B and A bar and S. And that would be one way. But instead of doing that, I want to have a more simplified product term that has fewer inputs to it. And I circle both of them, and I get B and S, which is that lower AND gate there. Yeah?
So for Sam, the furthest 6 blocks on that would be 1 for A or B.
Oh, right, right, right. If we were just going to do A or B, this and this would both be 1, right? Which is not the case here. That's absolutely right, and that's what the difference is. Okay, great. So here's how the selector can be implemented as a sum of products device. But what I want to talk about today, after we take a look at this circuit here, which is again the invert and an OR sort of 3-level sum of products form, is what might happen when S makes that transition from 1 to 0. And let me actually write on the board here, since I'm trying to get this right, which is P1 and which is P2. So let's see here. This is really fun stuff. I'm sure you guys are going to love it when you see this, because this is a fun topic, and actually the topic on Monday is probably the best topic of the whole class. So let me see if I can get this right here. After which it's all downhill. And so now I want to ask the question, what happens if both A and B are 1? So this is going to be a logic 1. This is going to be a logic 1. And S over here is going to go from high to low. Okay? It's going to go from a 1 to a 0. In other words, I'm going to switch from choosing this one to go through to choosing this one to go through. And what that means is that I'm going to start out with both of them being 1 and P1 being a 1 and this one being a 0. Okay, because if this is a 1, it propagates through here to a 0 and that becomes a 0. And then I'm going to switch S. I'm not going to change these guys. I'm going to drop this one down, which will turn this one off and turn this one on. Right? Because I'll switch. And basically I'll be saying, okay, stop letting B through and start letting A through. There's 2 gates, and I'm questioning which one is going to be open. Think of the selector as being made up of a whole bunch of gates, each one gating each of the inputs to say which one gets to race to the output. And then an OR gate which combines them all in the big race. Okay? So there's a bunch of mice here, right? And then there's these little gates that let the mice go through. Okay, what's the trouble? The trouble is that this path over here to shut off P1 involves less logic than this path over here to turn on P2. And so if I think about this as kind of P1 and P2, let's think of this eraser as the OR gate. Okay? If P1 is high, the OR gate is high. If P2 is high, and I do this right, the OR gate is high. Or if both of them are high, the OR gate is high. And if both of them are low, the OR gate's low. Well, the trouble is that here we are with P1, and P1 is going to drop off, and then P2 is going to pick up. And during that small period of time, when we switch from this one being in charge to this one being in charge, what's going to happen to the output? It's going to have a little glitch going down. And so a selector given 2 inputs, A and B, both of which are high, which is told first, choose B, and then next, choose A, may go through a transition where Q, which you see over there on the board, goes from high to low and then back to high again very, very quickly. As the internal circuitry of who's in charge of holding this output up goes through what's called a timing race. Okay? there's a race between turning this guy off and turning this one back on. And in general, computers inside are filled with problems like this. The technical term for this is actually, it's called a hazard, okay? Like a road hazard, okay? And in particular, this kind of hazard is called a 1-1 hazard, meaning that we started out with an output at 1, and we ended up with an output of 1, and we generated a hazard. Now, the reason I'm talking to you about the selector and about these hazards is that we're going to use the selector to implement a device which will then be used to implement the flip-flop or the register that we're trying to make. So I'm kind of building in this little section from the bottom up from the selector and how we understand how that works. And I want to understand the timing of the selector because ultimately we need to understand the timing of the flip-flop. So we all understand now, I think, that these hazards can happen. In general, there are 4 kinds of hazards that happen in computer systems. We're only going to worry about one of them. We're going to worry about the 1 hazards, the 1-1, where we go from 1 value, it glitches low, and then it goes back again to a 1 value. There are also hazards that go from 0 to 0. Turns out you get those when you do a product of sums form as opposed to a sum of products form. It's exactly the dual. And there's also other kind of hazards which are called 0-1 or 1-0 hazards that look like this and involves a kind of a hesitancy in terms of making a transition between a 0 and a 1 where it sort of bounces up and down a few times. Many of you have, of course, had experience with pressing the set buttons on a clock. Like, you know, there's a set button here to set the minute and the hour, and if the switch has a little bit of dirt in it, right, then the clock suddenly jumps a whole bunch, right, because the set button has kind of gone up and down many times in order to, you know, increment something. That would be a hazard that's kind of like this, okay? We're going to talk about why these things don't matter in general and why these things can't happen, but we are going to address these 1-1 hazards. Okay. Well, if we think about what we learned before in terms of contamination delay and propagation delay, or the TPD min and TPD max, then what we should expect that this device does is, first of all, we have 2 high values going in, and the selector, in this case, is going from low to high. Whether it goes from high to low or low to high doesn't actually make a difference. We know that it takes time from going from the low value to the high value, and during that intermediate time, we don't really know if the selector is a low or a high. But what we do know is that as soon as the select becomes contaminated, in other words, it's no longer a 0, but it's on its way to become a 1, then after the contamination delay, we expect this output Q to become contaminated, to become like this blue zone over here, meaning that the signal has a value that may not be a 0 or a 1. It may be some intermediate thing, and we don't know. And then only after this S has become a nice valid high value over here, after the propagation delay has passed, the TPD max has passed, then after that time can we ensure once again that the Q is going to have a valid high value. So in general, first of all, TCD is usually less than TPD, and furthermore, there's also this time that it takes for S to go between being a 0 and a 1, and you add those times together and you end up with this sort of time of indeterminacy in the usual specifications of a logic device. Remember, no logic device can figure out anything instantaneously, and what you learned the last time and practiced a little bit in recitation is that it's even worse than that. Because when a logic device switches between having one valid output and another valid output, not only does it take time for it to figure out what the new answer is, but first of all, it takes a while to get rid of the old answer, and then there's a length, that's this time here. From here to here is the time to get rid of the old answer, right? And then there's this time here while it's kind of figuring out what the new answer is and still trying to get it right. And then finally, it gets the new answer and has the new answer. So there's always going to be this blue time in the middle where for a standard logic device, we don't know what the output is. And so the fact that there's a glitch during this time is kind of to be expected. Okay, it's okay. And in general, in most logic devices, we're not going to expect them to perform any better then to, if the inputs are valid, the output is valid. And if the input changes, then we go through this indeterminacy time, and then finally the output becomes valid again with the new output value. However, yeah?
I thought we had said the propagation delay included the contamination delay.
If the slope of this line is infinitely sharp,
Okay.
if this instantly goes from a 0 to a 1, then yes, they both start at the same time. I'm getting a little more sophisticated here, okay, and let me maybe write exactly the formal definition. I didn't want to get too formal before, but maybe now's the time to do it. So the contamination delay T sub CD, which is equal to TPD min in most uses throughout the world, is equal to the minimum time from invalid input to invalid output. And what does that mean? We assume both A and B are high here, so they don't even count. S is the only input we care about here, and S is a nice valid low value here, but it begins to climb up and to get into this intermediate zone where we're not sure if it's a 0 or a 1, and at a certain point we decide, okay, it's not this valid, strong logic 0 anymore, and so we say S becomes invalid here. So the minimum time from when this becomes invalid to when the output becomes invalid is the contamination delay of the circuit. Time from garbage in to garbage out. Okay. On the other hand, the propagation delay, T sub PD, which is in the rest of the world TPD max, is equal to the maximum time from valid input to valid output. Okay? And so we measure TPD max, or TPD, by saying when does S, if it takes some time to go from low to high, finally become the valid new value here, and when does it finally come out with a valid value on the output here. And this is the longest that that could take. And this time here would be the shortest that the contamination could happen. So this is from garbage in to garbage out, from new value that's valid in to new value that's valid out. And that's why here we're starting to show you that signals don't transit instantaneously from a 0 to a 1. In fact, they take a little bit of time. And we're just kind of starting to hint at that. And in the class, as we go on and get deeper and deeper into the circuitry, you're going to see how that slope, in fact, comes about in natural circuits. But it kind of makes sense that you couldn't instantly go from a 0 to a 1. If 0 is a low voltage and 1 is a high voltage, it takes time to go from one to the other. Yeah?
I'm unclear why 1 is done in terms of min time and why 1 is done.
That's an excellent question. In general, what we care about in our circuit is that the contamination doesn't get through too fast. Do you remember the hold time thing, right? We don't want the contamination to race around the loop before the hold time is up. So circuit designers in general worry about, will the contamination get to me too soon? And so the question is, what's the smallest amount of time for the contamination to start to race around the loop? One could say, what is the maximum amount of time too? One could measure that. But in general, it's not a measure that's very useful. What we care about mostly is how quickly will we lose the old data going around the loop. Whereas with propagation, remember how that was used. That was used to figure out how soon can I clock the circuit again and make use of the output. And there the question is, over the entire temperature range, over all kinds of different parts, things like that, over different data, what's the longest that it could take for the new valid value to get there, so that I know when to wait until I clock it the next time. So that's why that's in general measured in terms of the maximum. Yeah. Oh, I thought you asked a question.
Okay, I was trying to do, yeah, can you articulate what is the meaning of the intermediate range? Because you seem to have defined two time ranges that have an indeterminate intermediate portion.
You mean this blue time here, or?
Well, it seems that there's an overlap between the two ranges, where one ends and the other one starts. where TCD, the bottom range, and
Where this one ends and where this one over here starts?
It seems to be an overlap. Or am I-
Oh, well, but that's okay. See, this is the input to the function, and this is the output to the function. And so I'm just plotting them on the same timeline. It's not that these are the same wire. So it's okay if something is going on here while something here hasn't started yet.
Okay.
Okay,
I
so
thought it might help us understand.
yeah, it turns out that you can figure out the time where the hazard might take place with this. Okay, if we were given the specifications for the device in terms of TCD and TPD, what that would say is if a hazard is going to take place, it'll happen somewhere during this blue time here. Okay, and so that's what the meaning of the difference between when the TCD is up and when the TPD is up. That during this time on the output, kind of all bets are off. We don't know what the output is going to be because we only guarantee that we'll hold on to the old value of Q up to here, and we only guarantee that we'll start putting out the new value of Q over here. And in between those two times, in general, in logic circuits, we don't guarantee anything at all. Okay? All right. Now,
Is there a difference between PD and PD max?
if you just say TPD, that's sort of, let me try to, so you know there's scheme and then there's the rest of the world, right? This is the MIT lingo, and this is the rest of the world, okay? Okay? That's basically what, I happen to like these, of course, but this is what the rest of the world uses. Okay.
If TCD isn't
Whoops.
included in TPD, why is it called TPD min for TCD? I mean, it would make sense if TCD was,
If it was actually part of it. Both of these things are due to the effect of signals propagating through a circuit. Okay, the question is what kind of signal do we mean? And in general, a signal goes from being a 0, okay, and then crosses a certain threshold where we say we don't know what it is. And then it goes and crosses another threshold. We say, okay, now we know that it's a 1. Okay? And during this time, we say it has an intermediate value that we're not sure of. And so the idea is that here is where the contamination starts to go into the circuit. Okay? And so we measure the TCD from the time when things go from valid to when they first become invalid, and then they become valid again. Any signal is going to go through these three phases as it switches from a 0 to a 1. From valid to invalid, back to valid once more. And so the question is, if I have a circuit and I feed a signal like this to it, how long does it take between when I no longer am sending it a 0? This is the old value, and here's the new value. And the circuit is, given the old value, it's producing an old result. How long after I no longer feed it the old input does it still produce the old result? Well, the answer is that it guarantees it will continue to produce the old result for at least TPD min, the minimum amount of time to propagate through the circuit, the minimum amount of time for invalid stuff to propagate through the circuit. And then the question is, okay, once I finally send it the valid new stuff, how long does it take for the valid new output to happen? And the longest that could take is TPD max. So there's sort of two concepts being mixed together here at the same time. One having to do with whether we're measuring time from invalid in to invalid out, or from valid in to valid out, and whether we're doing a measure of min or max. And it turns out that we only care about the minimum for the invalid inputs, and we only care about the maximum for the valid inputs. And that's why they're paired up in this way. There aren't 4 possible things to measure, there are only 2.
Is that the only reason why the TPD is usually larger than the TCD? Because we're worried about the max versus the min? Because
Let me,
the same thing, right? The time it takes data to percolate through the circuit and then
Yeah.
show up. Why is one larger?
Why is one larger than the other? It's actually a difficult question to answer. Let me see if I can give it a stab here. Okay. Let's say I had a circuit that was made up of units whose time delay was all 1. Okay? And here's the input, and here's the output. Okay? Oh, I'm sorry. Let's say I had a circuit who had two paths through it, one of which had a time delay of 1 and the other which have had a time delay of 2. Okay? How long does it take for a contamination or any kind of value here to go from in to out? Well, the minimum time it takes is 1, 2. The maximum time it takes is 1, 2, 3. Okay? Now, so that would kind of indicate that TPD min for a circuit like this is 2, and TPD max for a circuit like this is 3. Okay? Which is absolutely true. But it turns out that in designing circuits that use the data that flows through here, that do timing on the data that flows through here, when we're worried about how fast data goes through, the TPD min, we actually are concerned about how fast invalid data goes through. So that's why, in general, TPD min is a measure of the invalid time to the on input to invalid on output. Whereas when we're worried about how long it can take at most for the data to go through, we care about how long it takes the valid data to go through.
Is
Okay.
it right that there's not actually a causal, like it's not because it's invalid that it's faster or slower. It's just because
No.
we're measuring mins and max.
It's because we're measuring mins and maxes, that the max is usually bigger than the min. Right? It may be the same. But in this circuit here, the max is 1 bigger than the min.
Don't we have to get the new valid data in before we can be to the end of the TD?
Well, but at the same time, if this is the in and this is the out, and the amount of time they spend in this regime is the same, then measuring from here to here and measuring from here to here would not necessarily give you different times. From invalid in to invalid out, from valid in to valid out may in fact give you the same time. But there is this business where we're measuring the shortest time it'll take and the most time it'll take. So in general, TPD max will be bigger than TPD min.
Using this chart,
Yes.
suppose the slope of the rising S line were considerably more shallow.
So if this was very, very slow. Yeah.
Could not TPD max be less than TPD min?
It would shift over. This whole thing would shift over. Let's say that this would go out like this. Then we would begin to measure TPD max from out here. And this blue thing would keep on going until...
And the blue thing has to go as much as the shift in the...
That's absolutely right. Because it begins after the TCD has passed, which is measured beginning at this point. And it ends after the TPD max has passed, which is measured from this point here. So if you were to feed a very slow input to S, you're absolutely right that the time in which the output was indeterminate would be longer. But it would not change the TPD max or TCD or TPD min of the circuit itself. It would just change how long the output was in an intermediate state.
Would it be so awful if the output was unknown during the time that S was unknown?
It would not be bad.
It wouldn't.
In general, it's okay for this to go on. This sounds like an awful thing, right? After all, my God, the circuit's blue. You know, the wires are blue. That must mean bad things, right? But it's actually okay. And inside of your computer, at any given time, a lot of the wires are in these intermediate states. And what's great about it is that the succeeding circuits are not looking at the wire when it's doing that. If you remember our finite state machine timing diagram, that D flip-flop, the D register, did not sample its input until after all of this blue time was done. It waited until the TPD max had finished of one circuit, and then the next one, and then the T setup was done, and then we triggered it. Okay, so it's okay for these glitches and stuff to go on, as long as we're not watching the signal when it's going on. Okay. Does it sort of make sense?
The left side of the blue box
Yeah.
has nothing to do with the top of the slope of S.
Correct. Only has to do with the beginning of when S begins to go up.
So
That's absolutely right.
Move the top of the slope far to the right.
Right.
Why can't I have TPD max?
Because TPD max is measured from the end of the slope.
Right.
So this whole thing shifts over. There is no relationship in this picture here that says TPD max is more than TPD min. Nothing in this picture proves that.
Right.
Okay? I'm telling you that in general, TPD max is bigger than TPD min.
Would it be min less than TPD min?
Because we've inserted this difference between valid and invalid, according to that definition, one could imagine a circuit in which that were true. In truth, there are no circuits like that, okay? But from what you guys know so far, there's no reason to believe that the max should be bigger than the min. Except that it is. Okay. And you'll see why later. Okay. It turns out, despite the fact that I've been teaching all about this blue stuff, that if you really cared and you hated the blue stuff, you can build a selector that doesn't do it. And I got to this idea of an output that didn't glitch a little bit at the very end of the last class. We talked about a register, a flip-flop, that if it had a high output to begin with, and you clocked it, and it was meant to have a high output afterwards, that its output did not go through a little blue zone of perhaps glitching, but instead stayed high. And that's called hazard-free. Now, as it turns out, an hour and a half ago, at the end of my 6001 class, I went and I got a Coke out of the Coke machine, believe it or not, and something went wrong, and it gave me 12 Cokes, okay? So exactly the situation I talked to you guys about in the last class, and I was sitting there just laughing hysterically. Because you know, come, yes, and as I pulled one out, the next one came out. And what was just amazing is that apparently there's some safety circuit in there that says, uh-oh, I'm probably not supposed to be giving out 12 Cokes. Because after like the 12th one, it gave me all my money back and like cleared the whole mechanism. And then it just said, okay, well, let's just start over. So I got 12 free Cokes. I didn't even pay for one. But
your teacher taught you how to do that.
well, I wasn't using any technique that I had learned before. And so I left, all but one of them there at the base as a prize for whoever comes there. But in general, we're going to talk about this very special way to make circuits hazard-free. Okay? This is not in general used, except it is used occasionally when we are very careful about what the output should be. For instance, if it's going to a solenoid, which is a magnetic device, to allow a Coke to go down, and we're switching from one state where it says no Coke to the next state that says no Coke, we don't want to go through this glitch which says, okay, Coke, okay? The same thing with, thing with wires hooked up to your heart. You don't want it to go through some state saying, oh, let's just go ahead and zap the guy, just because we're going through this. So
this would very much be the exception?
This is the exception rather than the rule. And the reason I'm going to talk about the exception is that we're going to use the exception to build a flip-flop. All right. Well, it turns out that the exception is an extremely restrictive one. We're only going to guarantee that an output of a logic circuit is hazard-free under a very specific condition. And what the condition is that only one of the inputs is going to change at a time. In other words, if the output was supposed to be high, and only one of however many inputs there are change from 0 to 1 or from 1 to 0, that change can take as long as you'd like, okay, but only one at a time. Meaning that if we want to have two at a time go, we're going to leave at least a minimum amount of time called the width between the change of one and the change of the other. Let's not worry yet about what this width might be. But I just want to put in context, not only is this going to be an exceptional thing to do, we're going to be really restrictive on what we promise. What we're going to promise is not to glitch when one input changes at a time. If more than one changes at a time, if both of these guys change like this, then all bets are off. We might still glitch. Okay, we're only going to solve the problem for this specific case. Again, let's take a look at the K-map and the circuit that does it and how we might fix it. Before, we had one AND gate corresponding to one of those circles and another AND gate corresponding to another one. By circle, I mean the rectangle here. Another AND gate corresponding to the other rectangle there. And I talked about how the OR gate is sort of when the one product term holds it up like this and the other product term holds it up like this. And what we're going to do to solve this problem is we're going to add a third AND gate right here in the middle. And it's going to be A and B, and the output is going to go to the OR gate in combination with the other ones. Now, just to prove to you that I haven't messed up the logic, let's take a look. What is A and B on the K-map over here? That's this circle right over here, circling these two. And what that means is that when A is true and B is true, we're not going to be depending on these P1 and P0, or P1 and P2, these two gates here, to keep the output up. There's going to be a third one, and I don't have a third hand here, but there's going to be a third one, A and B, that's going to hold it up all of the time. And it doesn't matter that this one's going up and down, and the other one is going up and down. And this circuit is going to be hazard-free. Let me see. Do I have a picture of this? No. Okay. Let me draw this on the board here. We're going to put another gate in here. I'm going to take A and put it into there, and we're going to take B and put it into there. And if A is high and B is high, we won't care about these two gates here. We'll just keep the output high all the time. And I think you can see that that will get rid of the hazard, because there will be this middle gate that's going to hold it up during the transition of the other two. Now, why is this circuit hazard-free? The circuit is hazard-free because when I look at the K-map, let me get this exactly right here, like so. I used to go like this, I used to go like this, and now I'm going to put in another one that looks like this. You remember the rule of the K-map was that if I change one input, I move across one boundary. And what I'm saying here is that if the output is high and one input changes, I move across this boundary, but I stay within the confines of an AND gate that is not sensitive to the change. Let's say exactly which one this is. This is A here, this is B here, and this is S over here, okay? So what is this AND gate here? This is B and S, doesn't care about A. Where's B and S? That's this one down here. So this is this guy, that's this guy here. When A changes from 0 to 1, as long as B is 1, the output will not glitch, because I make this transition here, and that bottom gate stays on during the transition because it's not looking at A. And it holds the output high with a 1 value, regardless of how many times I wiggle back and forth across the border. So this circle says I'm hazard-free across the boundary here. Now how about when I go between here and here? Well, before I was not hazard-free. Before, if I switched S from this state from 1 to 0, and A was high and B was high, I might have a glitch because I was leaving this AND term, and I went through an intermediate zone where nothing was holding the output up as I crossed the boundary, and then I entered the zone of this AND term, which then held it back up. And during that short time, there might be a glitch on the output. So I fixed the problem by adding another island here, which doesn't care about S. And so when I transit from this state to that state, this middle gate isn't even looking at S. And so it is responsible, and it holds the output up, irrespective of the transition that's happening here. And I can take forever to make this switch. It can be a very slow slope. It can oscillate up and down. Doesn't matter. The wire doesn't even go to the gate. That's what it means to have a circle that has more than one 1 in it. It means that we're eliminating inputs from the product term. Then when I go across this boundary, same deal, except that I have a circuit that doesn't care about B. It's A and S bar, this one up here. It is intuitively obvious, that I cannot get a 1-1 hazard as long as there is a continuous path of stepping stones of these islands such that I never have to leave one before I enter the next one.
But with that very same circuit, you could get a 0-0 hazard.
Well, that's a good question. Can I get a 0-0 hazard? It's an excellent question. Let's say I'm here, and I translate to here. Well, 0 means I'm not on an island to begin with. None of the gates are going to fire. And now I go to another place where none of the gates are going to fire. And furthermore, only one input changes at a time. So of all of these gates, okay, let me take a typical AND gate. Before, it had a 0. Afterward, it had a 0, correct? And only one of the inputs changed. So these all stayed constant, whatever they were, and one of them changed either from a 0 to a 1 or a 1 to a 0. What must it mean for it to be true that before it was 0 and after it was 0, and one of them changed? it means that at least one of these guys must also be a 0. Right? I don't know about the other ones, but at least one must be 0 both before and after. Because here, this one's a 1 and this one's a 0. It's the only one that changed. The rest are constant, because that's the conditions under which we're operating. At least one of them was held at a 0 and did not change. So did this output actually change between these two states, or did it guaranteed stay low? If I have an AND gate and I hold one of the inputs low all the time, these things can wiggle up and down for all they want. Nothing's going to happen. So, as strange as it may sound, a sum of products implementation can never generate a 0 to 0 hazard. Okay? It can't happen.
The final gate's an OR gate, not an AND gate.
The final one's an OR gate, but to start with, everything was 0. Correct? Because the output was 0. And to end up with, everything was 0, because the output's a 0. And I just got through proving to you that for each one of these guys, they didn't glitch. So how could the output glitch? It can't. It's an amazing thing. So sum of products cannot generate a 0 to 0 hazard. Now, it's almost true. Okay? You see, I'm still getting that quizzical look, right? Here's where...
It can occur when we're going up through the change in S gate.
Except that if this changes from a 0 to a 1,
Yes.
and it was 0 before and 0 after, which is what we're stipulating, then this must be a 0. And if this was a 0 throughout, then this thing can't glitch. And that's true throughout the whole circuit. It turns out that there is one degenerate case, okay, which doesn't matter, which is if I have a AND gate and I have an input, let's call it X, and I feed it both X and X bar at the same time. Okay? According to the definition of sum of products, this is legal to do. Okay? And in this case, we have a single input change, which would result in a double input change to the AND gate, which could result in a glitch on the output. However, would you ever want to do this? Does this ever make sense to put A in A bar? No. Okay, so this might generate a glitch. Technically, it is sum of products, but there'd be never a reason to do it. So for any practical sum of products logic circuit, you can never get a 0 to 0 hazard. Again, for single input change. Single input change. And if you cover the path with AND terms so that there is never an interruption of these circles as you transit around, you can never get a 1 to 1 hazard. Now, in terms of what happens when you go to 1 to 0 and 0 to 1, we're not going to talk about that. That may, in fact, glitch all over the place. But we won't worry about that right now.
What may glitch?
If you do 0 to 1 or 1 to 0, okay? Let's not talk about it right now, because what it actually involves is the question of how many AND terms turn on when you go across 1. Whether there's, like for instance, when you go from here to here, there are 2 AND terms that turn on, and exactly what happens in the dynamics of the turn on and stuff like that. I could argue and probably convince you that that can't happen either, but I don't want to do it because it turns out 0 to 1 and 1 to 0 hazards are actually an ill-defined thing anyway, okay? And it's the subject of a paper that I have half written, so I'm not going to bother to talk about it. They don't really matter, okay? But these 1 to 1 and 0 to 0 hazards do make a difference, and I want to explain how they work.
So if you switch the switch, this is hazard-free. If you leave the switch and you switch, so if you leave it on B, or B determines, you switch B from a 0 to a 1.
It's actually hazard-free for everything.
That's also hazard-free as long as it's a 1 input.
Right, right. If only one of the, like I don't need to know what these 3 things are to tell you that this is a hazard-free circuit.
And pacemakers are built to be hazard-free?
Oh yeah, for sure. Okay. So in order to make sure that a circuit is hazard-free, here's the rules. First of all, don't use X and X bar as a single product term, like I showed you down there at the bottom, okay? Cover all adjacent ones in the K-map with at least one product term. That ensures that there's this continuous path where at least one of the AND gates will hold the output high during a transition of a single one of the inputs, And remember that this only applies if one input, single input change, one input changes at a time. If two change at a time, then all bets are off. We're being very restrictive in terms of this hazard-free business. Okay. So let's start to build some memory out of this thing. Okay? We have in our hands a hazard-free selector. Kind of a cool thing. G can go up and down. We've called SG now. And into the one input, I'm going to feed a data input called D. And out of the output of the selector, I'm going to take an output, and I'm going to call it Q. And here's how it works. Okay, we're building the memory here. Yay, yay, yay. Okay. When G is high, when the gate is high, the output Q is going to do what? Well, if G is a 1, then D gets steered to Q, and the output follows the input. So when G is high and D wiggles up and down, Q wiggles up and down, because the selector has chosen D. Q equals D. Of course, it's a short time later, but let's not worry about that for now. What happens when G switches from 1 to 0? Well, let's say that we used to be in the state of having the output be 1, because D was 1, G was 1, and Q was 1. And then suddenly we drop G right in the middle. Q stays high. Why does Q stay high? Well, because there is time delay in the circuit. And what happens is that the 1 comes out here, comes around back to here, gets chosen, goes out here, goes around and around and around and around. And positive feedback is going on here, and this thing latches in the 1 state. Okay? Alternatively, if we raise G up again, then the output follows the input. Then we wait for the input to be low and we drop G. Then it will latch in the low state, because we were looking at D when it was low, and this was low, and this was low, and then we just did this transition like this, and it was still low, and now we're no longer sensitive to D, but we're holding on with a positive feedback loop onto the low value of Q. So we can remember what D is. Now, we don't have a register yet, okay? We don't have this flip-flop that's sensitive to edges. We're building something more primitive, which is this thing called a latch, a transparent latch. Now, why is it called a transparent latch? Because when the gate is high, it's like a window, and Q is a transparent copy through glass of D. Okay? However, it latches when G goes low and holds on to whatever the last value of Q was.
What does G stand for?
G stands for gate. It opens the gate, the data flows through the window. Close the gate, and it holds on to the stuff. Okay? So it's an amazing circuit. It's an amazing circuit because it can remember stuff. After we have switched G from high to low, we don't care what D is anymore. It remembers this old value of D, which was present at the instant when we closed the gate. And the reason that we can be sure that it works and that it doesn't somehow lose the information when we suddenly switch G from 1 to 0 is because the circuit is hazard-free. Why is that? If D is, let's say D is high and Q is high, so we're going like this, then this will be high and this will be high and the feedback will be high. So all of these values have 1s on them. And the only input we change is G. We only just drop G from high to low. As this thing slowly switches from one to the other, what's going to hold this output high during that time? This AND gate in the middle. Because A and B are both high, and this guy's going to keep it high, and the feedback will continue to work, and we will not glitch when we suddenly change G from a high to a low. We won't generate a pulse on the output. We would be in trouble if we did. If when we suddenly said, okay, switch from being transparent to latching, if during that time, if during the switch, we generated a glitch on the output, then instead of holding on to the high value here, maybe the glitch would start to circle around and around and around. And that would be bad. We wouldn't know where we'd end up. But because it's hazard-free, this circuit will work. Yeah?
But wires have resistance, and so these voltages are continually bleeding away.
Absolutely.
So we can't be having, we can't just send it going. We have to have some way to...
Absolutely right. If I built this selector out of a physical switch, like a knife switch or, you know, toggle switch and I just hook that wire from the output back around to the input, of course the wire's not going to sit there at a high voltage all by itself. But it's not a wire. It's a set of gates. So this A is going to come through a logic gate and another logic gate and go and be wrapped around. So there are electronics that are in the path. And as we're going to learn about in class next week, these electronics actually have some amplification to them. And they will enhance the signal as it goes around and around and refresh it and keep it up there as a high, just like the memory system did that we talked about, where it measured the amount of water in the tub, right, and then added more. These signals here, if this begins to droop down, will pump it back up again as it goes around and around and around. Yeah?
So there are actually power leads?
There are power leads also, yeah. Here's ground, here's plus 5 volts, for instance. Yeah, now it makes a lot more sense than just, yeah. Yeah, there's actually power going into the whole thing. Yeah, this thing needs a battery to run, you know. We're actually going to get into some deep physics as to why, okay? But you can kind of see a little bit of a hint as to why. Okay, cool, huh? So now you know how to build a latch out of gates, which is pretty neat. In future classes, we're going to talk about how to build gates out of transistors. But for now,
What's the latch used for?
well, in this case, it's just used for storing things.
Just memory?
Just for memory. And it is sort of the most primitive kind of memory. But in a few seconds, we're going to show how to take a latch and build a flip-flop out of it, out of 2 latches. Okay? Okay. The state diagram for a latch looks like this. Now, this is a state diagram that is different than the ones you've seen before. It looks the same, except the difference is that this one has no clock. Okay, this is what's called an asynchronous state diagram without a clock. And the state that the latch is in is either in a 0 state or a 1 state. If it's in the 0 state and the gate is high and the data is high, it will switch to the 1 state. If the gate is high and the data is low, it'll switch to the 0 state. And it'll go to whichever of these 2 states the data says to go to, as long as the gate is high. As soon as the gate goes low, however, it stays in this state. Or it stays in that state, depending on the last state that it got trapped in. So it's like a ball that can shift back and forth here, and as soon as the gate drops, it gets stuck on one side or gets stuck on the other side. So this is a good way to describe the operation. And why did I have to say OR D here? Because remember, these arrows have to be exhaustive of all the possibilities. And if you think about it, if the gate is high and the data is low, that's one of 4 possible combinations of G and D. And it turns out, if you think about it, these are the other 3. If the gate is low or the data is high, then we stay in this state. Those are the other 3 possible things that we could do. And the same is true on the other side. Just to get an idea of sort of how you can use state diagrams to show how the circuits work. Okay. These fundamental mode state machines, these asynchronous state machines, this is a different word that we call it. We call it a fundamental mode because it's the most primitive kind of state machine there is. It has no clock. First of all, there's a finite number of states. The output is a function of the state and the input, just like we had before. If there's no input at all, it may just be a function of the state. And the state transitions occur asynchronously without a clock due to asynchronous input level changes. If the input levels change from a 0 to a 1 or a 1 to a 0. And in general, the architecture is exactly that architecture that I showed you in the last class. And if you remember, that architecture was a disaster. We tried to have students at the blackboard, right? Adding numbers around and around with no delay inside of here. But what I'm opening up the magic box now here is saying that ultimately we build circuits that look like this. And what was the circuit that we just built? We used a selector here, and we had the output and the feedback be the same signal going back around like this. And we had no synchronizing element in the loop because we're trying to build that element. And so ultimately we build it just out of some logic and wire for feedback. And what went wrong on the blackboard was because we weren't at all being careful about how to time this thing. And what I hope you are getting a feeling for is that in this lecture we're being extremely careful about the exact timing of the signals that are going through here. We're considering contamination delay and propagation delay. We're considering hazards. We're looking at all the possible things that might go wrong in a circuit like this.
Well, what's CL here?
CL stands for combinational logic, same as before. And so the only thing that I'm going to teach you how to do here with these kinds of very dangerous circuits that just have pure feedback in them and no synchronizing delay in them is how to build circuits that can handle one input changing at a time. And I hope that you realize that in the case of the transparent latch, the way that we ensure that only one input changes at a time is to ensure that around the time that the gate drops from a high to a low, that the data does not change. Because again, let me go back here and show you again the picture of this thing. Here's the data going in, and here's the gate. These are the two inputs to the circuit, right? How do I ensure that these two inputs do not change, or these three inputs that I only change one at a time? Well, the only real control I have is over the gate here. And the answer is don't change the gate from high to low while the data is changing. And it turns out that that sort of limitation, saying only one input change at a time, is exactly the same as the thing we talked about in the last lecture, saying that there should be a setup time and there should be a hold time around the instant that a memory element needs to capture whether an input is a 0 or a 1. It's the same as saying that when you take a picture, you want the person to hold still. So when the gate is high, the output is going to follow the input data, whatever it is, 0 or 1. Doesn't matter. However, we know that we want the gate to snap closed and for us to go into the feedback mode and latch on to either a 1 or a 0. Around that time, let's make sure that the data doesn't change. And so we'll establish the setup time beforehand and the hold time after and say that this guarantees that only one input has changed at a time on that circuit, and thus the circuit is hazard-free, and thus it will be able to hold on to the value properly. And there will be no glitches trying to go around and around the loop, but rather just a constant value going around and around the loop. And so this is how we're going to build this latch.
I'm a bit confused because you were saying that the problem with the blackboard when we first tried, which was, if you like, an asynchronous mode.
Yes.
The problem was that there was no clock.
That's absolutely right.
We're going to solve that. We're going to solve that in asynchronous mode by being extremely careful about timing issues.
Right.
So what's the difference?
Well, the problem is a little different too. The problem before was we were trying to also calculate a number which kept getting bigger. The problem we're trying to solve here is much more simple. We're just trying to remember a 0 or a 1. And I guess the point I'm trying to get across is, in general, designing asynchronous fundamental mode state machines with feedback that does not have a synchronizing delay element is a very difficult thing to do, and it's a very difficult thing to get right. And so what I'm trying to get across is that what we're doing here is, first of all, we've narrowed the problem down to be almost the most trivial state problem that there can be. Remember a 0 or remember a 1. And then furthermore, in order to do it, we're going to establish all of these very strict conditions saying don't try to do it while things are changing. And then we're going to say, and in the circuit we're going to use is going to be such that if we obey all of those rules, then we can prove that it's going to work because it won't generate this glitch. And then we can see that the feedback is going to work. So I guess the lesson I want you to take away from this is we're being terribly restrictive here. Single input change, only trying to remember a 0 or a 1, and hazard-free circuit. Okay? And under those conditions, we're able to generate a circuit like this and be assured that it's going to work. But in general, circuits like this don't just work.
Because when you set up the system, you've made extremely conservative assumptions about all of the various things we've been discussing.
That's absolutely right. Now, we haven't talked yet about how you figure out how long the setup and the hold time are, but you can know, I think, that it's going to have something to do with that symbol T sub W we talked about a few slides back, which was how long do you leave in between when things change on the input to guarantee that it's hazard-free. In other words, the amount of time we need to leave for things to settle down before we change this one is sort of a measure of how long between a change here and a change there, or between a change here and a change there, which is a thing that's measured by what does it mean for only one input to change at a time.
Are setup time and hold time something that you like document on a memory chip?
Absolutely.
Be careful.
Absolutely.
Or is it something that's implemented where it has logic that prevents the switch, that prevents the switch from changing.
Ah.
Inputs have changed recently.
Now that's a really excellent question, okay? Which is a question is it possible to build logic to filter the inputs to a circuit to guarantee that the setup and hold times are going to be met? And that's going to be the subject of the amazing lecture on Monday, the best lecture of the whole class, okay? However, in general, the first thing you said is true, which is that when you buy a chip, it comes with some specs saying what is the setup time and what is the hold time. Okay, there are other fundamental mode circuits, and I'm going to very briefly go through these just so that you'll see them. One's called a set-reset flip-flop, which looks like this, and the state diagram looks like that. And I'm not going to bother to go through it in detail, except to show you the K-map for it, which looks like this, except I didn't show you that the other term is this guy here. Okay, it's hazard-free. It has one bit of feedback like this, and if only one input changes at a time, it's guaranteed to work. How the circuit works is that if you put a 1 on the set line, it goes into this state. And if you put a 1 on the reset line and you don't put a 1 on the set line, it goes into the other state. So this is actually one of the first flip-flops that ever came out, sort of like a teeter-totter. If you push on this end, it stays down there. Push on this end, it stays down there. Set, reset, flip-flop. Okay? It's just a transformed version of the transparent latch that we're looking at here, and the general notion of a logic circuit with one bit of wire feedback is exactly the same. And the reason it works is, again, because the K-map, which has this term in it, and also one more here, which I haven't drawn in, is hazard-free. So this is just by way of things. Here's other ways that people draw the flip-flop. It's kind of a cool thing to look at. In your spare time, you should kind of play with these things and see that they work the same way. It turns out there's really only one state machine. For a machine that has two states, to remember a 0 or a 1, that's hazard-free and works in this way. And basically, if you have a circle here and a circle there, you don't have any freedom at all in terms of how you draw the arrows. There can only be two arrows out of this state, one that goes to the same one and one that goes to the other one. And there can only be two arrows that go out of this state, one that goes to the same one and one that goes to the other one. So in general, all of these single-bit fundamental mode memory circuits have a state diagram that looks like this, whether it's a set-reset flip-flop, a transparent latch. There are all sorts of other ones. One's called a JK flip-flop. Anyway, one condition to set, the other one to reset, and if you're not doing either one of those things, you stay in the same state and you remember what the bit used to be. Okay, I'm not going to bother with this. This basically says that it's actually possible to design fundamental mode circuits that have more than one bit of feedback, like the thing we tried to do on the board, and that have not single input change as well, and to limit which hazards you care about and which ones you don't. And it turns out that you can do it, but it's a tremendous amount of work. And so in case you guys want to go off and become hotshot fundamental mode asynchronous logic circuit designers, of which there's a market of absolutely 0 people in the whole world, I guarantee you. You can read this book, okay? But for now, it's going to be good enough for us to handle the simplest fundamental mode logic circuit there is, and that is the single-bit memory. Okay, this shows how we can transform a set-reset flip-flop into a D-latch by putting some logic in the beginning to sort of map D and G into S and R. The memory is being done here. Here's the feedback kind of going through this thing here. And then the transformation from D and G to S and R are done here. This is only done to show you that really there's only one single-bit fundamental mode machine out there, and you can always transform the inputs from one to the other. I can translate a D latch, a transparent latch, into a SR flop and vice versa. This is a way of changing a SR flip-flop, which has a circuit that looks like this, into a D latch by putting some AND gates and inverter on the input. Nice way to think about this. If D is high and G is high, then the output here will be low, which this is set bar, so we're going to set this thing. And if D is low and G is high, then this output here will be low, so we'll reset the thing. So here's the teeter-totter, right? And whether we teet or we tot depends on whether D is high or low when G is high. But if G is low, then both of these gates are shut off, and we neither set nor do we reset. And we leave the teeter-totter alone. So that's, again, just to show you, if you come across set reset flip-flops, you'll think this is nothing new. This is the same stuff I learned about with the D latch. Okay, let's do the final thing here, which is going to be, how do we build a flip-flop? Well, a flip-flop's a little different than a latch. Okay, remember the latch, when the gate was high, it was transparent. D was transferred to Q as long as the gate was high. That's not true here. If the clock is high, D is not transferred to Q, nor when the clock is low is D transferred to Q. Rather, when the clock goes from low to high, D is sampled and transferred to Q. Now that seems like an incredibly hard thing to do. How could you take a picture of D kind of in an instant and not be transparent, not pass through D either when you're low or you're high? Well, let me give you a hint. It's the same question of how can you get the astronaut from inside the space shuttle to outside the space shuttle without becoming transparent to all the air that's inside the space shuttle and letting it all outside the space shuttle. And what's the answer? You use an airlock, right? You have two doors, two transparent latches, and you never open both of them at the same time. You let one open, data goes through to here. You close that one, open the other one, data goes out the rest of the way. And that's how we're going to build this thing. It's sort of an airlock for data, and it looks like this. The clock goes in here and goes through an inverter and goes to the gate of a transparent latch on the left-hand side. It also goes directly, without an inverter, to the gate of a transparent latch on the output side. Thus, when one is open, the other one's closed. When the other one is open, the other one's closed. In other words, thinking about the gates or the transparent latches like a set of switches like this, we go from a circuit with a topology like that to a circuit with a topology like this. Let's think this through. When the clock is low, this one here is high, so this one is transparent. Now the clock goes from low to high. This G goes from high to low, and this transparent latch holds on to the data. Simultaneously, because the clock's going from low to high, this one becomes transparent. And so whatever this one's holding on to gets sent through to Q. And thus we've sampled D and sent it through to Q. Now comes the hard part. The clock now goes from high to low. And we don't want to lose Q. So what happens? The first thing that happens is the clock goes from high to low. This thing, which was passing the data through before, grabs a hold of it and becomes responsible for holding on to it. And then, because the clock went from high to low, this goes from low to high. This one becomes transparent and lets the data through, but only up to here, because this guy is latching onto the data. And that's how you build a flip-flop. It's one of the ways. Isn't that cool? And it takes a snapshot at an instant because there are two latches in series with each other, controlled in opposite phase. All right.
And somewhere you put the enable in there so that you could
yes.
tell it.
How would the enable work? That's a great question. We're going to get to it in a future class. I don't think it's in this set of lectures.
A mux before the clock going in.
There's many ways to do it. Well, all right. I can't make you wait. Let's say that you had a register without an enable, and you wanted to make one with an enable. How about this? I put a selector here, 0, 1. I call this one D. I call this one E. If the enable is high, then the data gets shuttled to D, so that when the clock goes off, the new data goes in. If the enable is low, then the data is not looked at. Instead, the old output is shuttled back around. And then when the clock goes off, it sure does clock in something new, but what does it clock in? What it used to have, which is no change at all. So the way we're going to fool the camera into being off is we're going to put a copy of the film in front of the lens. Okay? Sounds really dumb, but it turns out this is the easiest way to do it. Okay? So that's how we're going to build E into the circuit. So now we're just talking about how to build this, and you've asked how to add E to the circuit. We'll show you that in a future lecture too. Okay, fun stuff, huh? This has a setup and a hold time too. And as before, remember it used to be measured when the gate went from high to low? Well, if we measure setup and hold when this gate goes from high to low, it's the same as measuring when this input goes from low to high, and that's where we get the setup and the hold time measured around the time when the clock goes from low to high over here. Yeah?
Does the fact that it in one case has to flow through a NOT gate and the other case doesn't present a timing problem?
Yeah, it turns out that you have to be a little careful about the overlap of the two G's here, okay? And in general, you want the signal on the second one to happen a little bit sooner compared to the first one. And if you want to, you can work that out. That doesn't matter right now. There's another style of clocking where you sort of make sure one of these goes off before the other one goes on, as you would in an airlock, okay? If you have these two doors, right, and one's going to open when the other one is going to close, what you really want to do is you want to close both of them and then open the other one, close that one, and then open the other one, close that one. And so the design of the circuits on the inside, the designers are very careful to arrange the timing in such a way that it is never the case that both of the G's are high at the same time. Yeah?
If you can do that on this, why couldn't you do it on the earlier one-to-one hazard state? Why do we need to build in the third AND gate?
Because if we dropped, let's see, the hazard, what you're talking about is the hazard that made it difficult to switch this thing here, right? We needed to do something when we were in the intermediate state. Okay, so what these circuits do when we're in the intermediate state where both G's are off is that they hold on to the old value there because they themselves are memory elements. A selector is not a memory element. So when you're halfway between one switch setting and the other, it doesn't know what to output. So what we're saying is that if you are halfway in between the two settings and both of the inputs are the same, output whatever that input is. Okay. I don't know if that's clear, but if there's more, you can ask me later. Okay, setup and hold times. Here's the other examples. The airlock I already told you about. How about the escapement in a clock? I don't know how many of you guys play around with these things, but there's this sort of mechanism in a old-style clock where there's a little wheel with teeth on it and a device that kind of rocks back and forth, and usually the pendulum is hooked up to here. So as the pendulum rocks back and forth, it goes click, 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 click. If you take the pendulum and you move it very slowly back and forth, that's the clock input. Do you think there's ever a case where this wheel can spin forward and the spring can kind of let loose and goes and the hands just go really, really fast? No. What this thing is doing is basically flip-flopping back and forth between being stuck on this one and being stuck on that one, and at no time is it transparent in such a way that these little teeth can keep going through the circuit as fast as they want. This is like one door of an airlock. This is like the other door of an airlock. And the escapement ensures that one door closes before the other door opens, so that it can only go forward till it hits that door. And then it goes like this, and it goes forward till it hits this door. And then it goes like this, and then another tooth hits this door. And then like this, and then it hits that door. And so the idea is that this pendulum is literally the clock pulse, which is allowing data items, which are the teeth of this gear, to go through at the clock rate, and that makes the hands progress at a fixed rate. And that's just an amazing thing, okay? And it never lets the thing just spin. Okay. Finally, we get down to the one that's the most fun here, right? This is a picture of a AR-15, which is the same as an M16, but only a single shot at a time. It actually has a flip-flop inside of it that is mechanical. And it is mechanical particularly in order to fire only one bullet every time the trigger is pulled. And here's how it works. You pull the trigger, right, and it goes bang, right? The bullet comes out, and a mechanism goes backwards inside of it, right? And if it weren't for the flip-flop in there, it's in a condition where, because it's a semi-automatic rifle, it has reloaded itself with the next round, and the trigger is still down. All this reloading of the next round happens so fast that your finger, if you're firing one of these things, has not yet lifted off of the trigger. So the question is, what stops the next bullet from coming out? Is this a transparent latch such that when you pull the trigger, it just keeps firing bullets until you let go? Well, if it's a M16, which the military uses, the answer is it's sort of like that, but it turns out that's not even true either. Okay? But if it's a single shot rifle, such as you saw Eve with there, it only fires one. And how does it know? The answer is that there are two little mechanical pawls in there. One's called a sear, it's S-E-A-R, and that lets the hammer fall when you pull the trigger. And another one is called the disconnector, and that's the one that holds the hammer back until you let go of the trigger. And it works exactly the same as the two latches that are on the inside of a flip-flop. One's sensitive to pushing on the clock, and one's sensitive to letting go of the clock. And in no case does it let more than one round through at a time. And if you ever have the pleasure of firing one of these things, and you know, if you do this for fun, it actually is lots of fun. It's an excellent rifle to shoot, very well made, and doesn't have much kick to it too. You will notice that when you let go of the trigger, it goes click. And the click that you hear when you let go is actually the sound of the flip-flop going into the other state. And then when you fire it, of course, it goes bang, which is, you know, the other state transition. But you do hear the state transition backwards too. And that's why only one round comes out at a time, because of a flip-flop. So now you know all this stuff. And I guess that's about it for today.